All right, 2.7. We are going to start picking up the pace here a little bit so we can start getting closer and closer to the end of the year, right? The faster we go, the sooner it'll get here. I think that's how it works. Yeah. All right, so 2.7 is the last differentiation skill we're going to learn for a while until we learn the derivative of particular types of functions. So what we've been doing so far has been, believe it or not, called explicit differentiation, which means when you get stuck, right, you curse, right? And so that's why they call it explicit differentiation, like, dang you, right, calculus. But now we're going to be doing implicit differentiation, which means we're going to be like going, right? We're not going to be cussing. That has nothing to do with what we're doing, okay? The reason that what we've been doing so far has been explicit differentiation is because if we have something like y equals x sine of x, this is a function of x, right? It's solved, we could say, for y explicitly in terms of x. That's what that means. We have y equals, and on the right-hand side, there are no y's. We were able to isolate our y, and we have a function of x on the right-hand side, which means when we graph it, it's going to pass the vertical line test. But not all equations are going to be functions of x, right? For instance, if you have a circle, or an oval, I should say, an ellipse, as we call it, what if you were representing some quantity that was represented by that equation, and you were still interested in how fast that equation was changing at a certain moment in time? They shouldn't be excluded just because they're not solvable for y as a function of x. They don't pass the vertical line test. They shouldn't be excluded, and they're not. So what we're going to learn in this section is how can we take the derivative of something that is not explicitly solved for y in terms of x. In other words, it's implicitly solved for y in terms of x. That method is called implicit differentiation. All right, so to start off, we need to kind of get this down. We've been taking the derivative with respect to x. X is our independent variable. So as x changes, we want to know what the effective change is in the dependent variable. So the derivative of y with respect to x, that is verb of y, is noun, dy dx. That's what we've been doing. It's y prime. We haven't been showing this, but the derivative of x with respect to x is 1 because when you write it as dx dx, these are the same differentials and they essentially divide out. So we haven't really been showing that. But that's why it's equal to 1. dx dx is 1. So let's take a look at this example. This is y equals 2 over x. That would be in what we call explicit form. You have a function of x. It is solved for y explicitly in terms of x. There's no y's on the other side. If you just multiply both sides by x, you get xy equals 2. That's still an equation, but now it's not solved for y. Okay? Now, if it can be solved for y, you're probably going to want to solve it for y and take the derivative like we've been doing. So like in this case, if I asked you to find dy dx, I would probably divide through by 2 first, solve it for y in terms of x, and then take the derivative. But not all things can be solved for y as a function of x. So what we're going to do is we're going to verify it, that we're going to get the same answer either way. And you're going to be like, cool, and then you're going to trust the method. So we're still interested in dy dx for this function here. Let's take the derivative of both sides with respect to x. So this is what we've been doing. I think when we first did this, I showed this step, and then I said you don't have to show it anymore. We're taking the derivative of the left side with respect to x, and then we're taking the derivative of the right side with respect to x, and I'm going to write that as 2x to the negative first. So that's what we've been doing. We haven't been showing that step. The left side then, of course, goes straight to dy dx. And the right side, by the power rule, we get negative 2x to the negative second. And when we clean that up, we get dy dx equals negative 2 over x squared. And that is, in fact, the derivative function. Pretty easy, right? Good review. Well, let's go ahead and do the same thing now for the same equation that is not solved for y. It's xy equals 2. I still want to find dy dx. I'm still interested in that. So let's take the derivative of both sides with respect to x. Just like we did above. We're going to show that step now. If it's not solved for y in terms of x, now we have to show this step. Okay, now what is going to be the derivative on the left side? What rule are we going to have to use now? I have to use a product rule, yes? Because it's x times y. So what would be the derivative of x with respect to x? It would be 1. Or you can write dx dx if you want. I'm going to go ahead and just write it as dx dx. So it's dx dx times y plus x times dy dx. Would you agree? Or 1 times y plus x times dy dx. Take the derivative of the first times the second plus the first times the derivative of the second. 2 factors generates 2 terms. What would then be the derivative of 2 with respect to x? Constants don't change, right? With respect to x, so that would be 0. Now remember, I'm trying to find dy dx. I didn't solve for y in the beginning, so now I need to solve for dy dx. Well, I can call dx dx 1, and so how do we solve for dy dx? We have to isolate that, so we get x times dy dx, and if I bring the y across, it becomes negative y. And now I'll divide through, and I get dy dx divided by x, and I get negative y over x. And there I have solved for dy dx, and if I compare it to what I got on example 1, let me come up here and grab that, they should be exactly the same. And this will prove that they are both viable methods, right? They are exactly the same, aren't they? Uh-oh, not quite. Notice the one that we didn't solve for y, the implicit version. We need now to evaluate it. We need to know both the x and the y coordinate. That's going to be kind of a common thing. When you take the derivative implicitly, you typically end up with both x and y. And here's the reason why. If you think about it, if I just drew a vertical line here, call it x equals 2. If I wanted to find how fast that oval was changing at x equals 2, you would be confused if I didn't specify the y value. You'd be like, you mean right here on the graph or right here on the graph? And would it matter what the y value is? Absolutely. It's not a function of x anymore. It's a function of both x and y. So that's why your derivative is going to have both x's and y's in it, because you're going to need to specify a 2-coordinate grid system. It's not just one x value anymore. But these two are exactly the same, and I'll prove it to you. If you take the original thing, xy equals 2, if you now solve it for y, you get y equals 2 over x. If you then substitute that in right there, you get dy dx equals negative 2 over x all over x, which when you stage change flip gives you negative 2 over x squared. So it does turn out to be the same. So if it can be solved for y on the front end, we're still going to want to do that because it's going to make the derivative easier. We can fall back on what we're used to, and it makes using the derivative easier because it only requires the 1 input instead of the 2 inputs. So what we just did is we proved that they are both viable methods, okay? So what we did in example 2 was called implicit differentiation. We're taking a full-on derivative, but we're doing it on an equation that is not explicitly solved for y in terms of x. And so we did it, they call it implicitly. Done. All right, so when we differentiate implicitly, this now becomes a requisite thing to show. If it's solved for y as a function of x, you can go straight to y prime or dy dx. No one's going to not know what you did. But if it's not solved for y as a function of x, we have to show that step. So it's a little bit of rewriting, but as you're doing that, you can kind of rearrange terms and put things in ready-to-go format. Okay, and here's where I would really not use y prime because it can turn into y to the first pretty darn easily if you're not paying attention. So I'll use dy dx pretty exclusively. It stands out a little bit taller, too, in your equations. This section is going to be some of the yuckiest algebra that we do all year. And by yuckiest, I mean delicious. Okay, depending on your outlook. It's going to require a lot of algebra. If you like algebra, you're like, oh, yum, yum. If you don't like algebra, you're like, ooh, yucky, yucky, gross, gross. But it's good for you, okay? So here we go. Example 3. For the equation y equals x plus secant of y, find dy dx. Okay, it's definitely an equation. Is it explicitly solved for y as a function of x? We have on the left y equals. That's a good start, right? But what do you notice we have on the right-hand side? We have a y. So you got to be careful. Just because it says y equal doesn't mean it's explicitly solved for y as a function of x. This is y as a function of x and y. First thing you want to consider is, can we solve it for y as a function of x? Can we isolate the y's? Do you think that's going to be possible here? No, because that y is trapped behind a secant. In order to spring him, we have to take the inverse secant of it, which means we're going to trap this y behind an inverse secant. No good. So how would we spring the guy that's trapped behind the inverse secant? We take the secant of it, which is now going to trap this guy behind a secant. And back and forth we go. So one of them is always going to be jail. So we're not able to solve for y as a function of x. But we still want to know, whatever this graph looks like, it can kind of look like this, right? It can look like this. And maybe that's what the graph of that looks like. I don't think so, but let's say it does. I might be interested in the slope of the secant line or the tangent line right there. I want to know how fast that snake graph is changing right there. So notice I would need more than just an x value, right? Because then I wouldn't know if I'm talking about any one of those four. So let's go ahead and find it. See you, snake. Delete. So first step is to take the derivative of both sides with respect to x. If you want to rearrange terms before you start, that's not a bad thing. Like if you wanted to get your y terms together on the left, you could subtract secant of y. Some people like doing that. That's fine. We're going to have to shuffle a lot of terms around anyway. It's really not any more difficult to shuffle around on the end. So we do that first. Now we take the derivative. So using the chain rule, the derivative of y with respect to x is just dy dx. On the right-hand side, what's the derivative of x with respect to x? 1. So the first term is done. If you want to call it dx dx, that's fine. Or just think of it as dx dx. It's 1. Plus, now here's why this section does follow the chain rule. That's essentially what we're doing. It's secant of blob. What would be the derivative of secant of blob? Secant blob, tangent blob, and then times the derivative of the blob with respect to x. Okay, so here's another way to look at it. Any variable that's y is going to generate a dy dx when you're done. Every variable of y will generate a dy dx. So you can kind of account for them. How many y's do we have in our original equation? One on the left, another one on the right, that's 2. So how many dy dx's should we end up with? 2. We have one on the left and one on the right. Okay? Now all we have to do is solve for dy dx. There's a little bit of work on the back end. And you should be always able to solve for dy dx because it's always going to be a linear function in terms of dy dx. So even though you can't solve for y, you can always solve for dy dx. So if we bring that red term from the right side over to the left, we get dy dx minus secant y tangent y times dy dx, and that equals 1. Now, how do we get the dy dx's by themselves? We have factor it out. Good. And remember, when you factor something out, you're left with just as many terms. Some people mess up on this very first term. It's an easy place to go wrong. What are we left with when we factor dy dx out of itself? A 1 minus a secant y tangent y. This is a good place for you to mentally redistribute it and make sure you get the line above. So that's pretty typical. We're going to expand everything out, collect our dy dx terms, then factor the dy dx term out. And then all we have left to do to solve for dy dx is what? Multiply through by that blob. So we get dy dx equals 1 over 1 minus secant of y, tangent of y. Now this is interesting. Notice your derivative is not a function of x and y. It's just a function of y. So it doesn't really matter what the x coordinate is. It only depends upon the y coordinate, which means our original function was not a function of x, but you could solve it for x as a function of y, which means it doesn't pass the vertical line test. It must pass the what line test? Horizontal line test, yeah. Now, I wonder what that graph looks like. On your 83s or 84s, you're not going to be able to figure out what that graph looks like. But with the power of the internet, we can. Y'all have heard of Wolfram alpha, right? If you just do a Google search for Wolfram alpha plotting in 2 variables, it'll take you to this handsome screen right here, plotting in two variables. So here's all we're going to do. We're going to leave the plot there, and we're just going to type in our equation. Okay, we're going to type in y equals x plus secant of y, parentheses y. All right, is that it? And now we're going to hit the equals button right here. And it's computing, 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 and it should give us our graph. So it's kind of grainy on there. Let's zoom in a little bit. That's what the graph is of, I won't say function, but of the equation that we just looked at. And notice, it does pass the horizontal line test, doesn't it? Fails the vertical line test. So this one is a function of y, not a function of x. So if you wanted to know what the slope of the tangent lines were at any given value, all you'd have to do is pick your y value and plug in a number. Let's see if we can use it once. What would be a good angle? Because y represents an angle, right? What would be a good angle to use here? Pi fourths? That's going to give us radicals. What about at pi? Pi would be a good one. So let's evaluate it at pi. Okay? Now, at pi, I mean when y equals pi. Yes? So here's how we show it in Leibniz notation. We put the when bar, and we just put when y equals pi. And then we plug it in, and we get 1 over 1 minus secant of pi times tangent of pi. And then if we simplify, what is tangent of pi? 0. And so 0 times secant of pi, which is -1, is 0. So we're left with 1 over 1 minus 0, which is 1 over 1, which is 1. So we can actually verify that. That's your 45-degree positive sloping line. So let's just see if that works. We'll come over here back to the graph, and we'll come up here to pi. There's 2.246, or 1, 2, 3, 4. Okay, so pi is going to be somewhere about right here. And if you come over right around there, can you imagine the slope of 1 being about right there? A 45-degree slope line? Yeah. Okay. So not everything in the world can be modeled with single variables, right? There's multiple variables usually in any system that kind of are responsible for the outputs. All right. So what we're doing is we're taking the derivative with respect to x. So if we change x, how does that affect our output? All right, very good. So there's your first full-fledged implicit differentiation. So when do we have to use implicit differentiation? When what? When our equation is not solved for y, explicitly for y as a function of x, okay? We always look to see if we can solve it for y first, because in the end that's going to be easier. But if we can't, we have this new method called implicit differentiation. We take the derivative of both sides with respect to x. Anything that's not an x is your independent variable. Any variable that's not an x is going to get a chain rule, d variable dx tacked onto it, in this case dy dx. Then we're going to collect our dy dx terms, factor it out, and divide back through, and we're done. All right, let's try another one. Example 4, find the slope of the graph of this dude at the point 1, -3 by finding dy dx first and then evaluating it. All right, let's take a look at him. What's up, dude? Is it solved for y as a function of x? No. Can it be solved for y as a function of x? The answer is yes, but not very easily. There is a cubic formula, like there's a quadratic formula, but the cubic formula is really, really big and really, really long, and I don't know what it is at the top of my head. Do you? No. Okay? So instead of using the cubic formula to solve for y, since we know we don't have to, let's just take the derivative. How? Not explicitly, but implicitly. So we'll take the derivative of both sides with respect to x. Now here's another option that you have. If you want to group your y terms, if you can, already on one side before you take the derivative, you can. It's y cubed plus y squared minus 5y. And then on the other side, let's just bring the x squared across. We'll take the derivative with respect to x. And so now we have a positive x squared minus 4. There's nothing against doing that. So it's kind of a 2-for-1 on the first line. You put ddx in front on both sides, and then do any rewriting that you need so that both sides are ready to go. How many y's do I have? How many terms? How many visible y's? 3. So how many dy dx's should I have? 3. Okay, here we go. Using the chain rule, what's the derivative of y cubed? 3y squared times dy dx. Very good. Because it's blob cubed, right? The derivative of blob cubed is 3 blob squared times the chain rule, the derivative of the blob with respect to x. So that's the derivative of y with respect to x. What would be the derivative of y squared? 2y times the chain rule, dy dx. Perfect. Minus the derivative of 5y is just 5 times the chain rule, dy dx. So you see, we're taking the derivative the same way we normally would. We're just putting a dy dx at the end of everything. And then on the right side, the derivative of x squared is what? 2x times the chain rule, dx dx. But do we need that? No, because it becomes 1. And then what's the derivative of 4? 0. All right, so at this point, if our dy dx terms were not already together on one side, that would be the next step. We shuffle them around in the beginning, which kind of does save a little bit. And now we factor out your dy dx. We're still left with 3 terms, 3y squared plus 2y minus 5 equals 2x. And then we divide through, and we end up with dy dx equals 2x over 3y squared plus 2y minus 5. So notice this derivative is a function of both x and y, meaning the original function probably failed both the horizontal and vertical line tests. It was like a circle or an oval or a snake graph or something. So you do need both inputs in order to evaluate it. They gave us the input, right? 1, negative 3. So all we have to do now is, with the right notation, evaluate it at. Now, if it's an ordered pair, here's all you need to do. You just write it down there at the bottom. You might see in some textbooks like x equals 1 and y equals negative 3. But you could do it like that as an ordered pair. That means you're plugging it in. Now you got to make sure you're plugging in the right number for the right variable. The x is 1, so we get 2 times 1, and the y is 3, so that becomes 3 times 9 minus 6 minus 5. Okay, if that were a free response, you could call it quits there. Let's keep going, though. That's a 27 minus 6, that's 21. 21 minus 5 is 16. So 2/16 is the same as 1/8. All right? So what do we know about the graph? It's hard not to call them functions. What do we know about the graph of that dude? Well, at the point 1, negative 3, it's what? Increasing or decreasing? It's increasing. It's only going up 1 for every 8 to the right, or up an 8 for every 1 to the right. I'm kind of wondering what that graph looks like, aren't you? Yes, y'all are filled with wonder like I am. So let's, go pro now? No, thank you. Why go pro when I don't have to? Let's come back up here. Y cubed plus y squared minus 5y. Use the little caret there for the exponent like you would on a calculator. Minus x squared, I'm typing in the original one, equals negative 4. All right, so I'm asking it to plot that. I hit equals, and sometimes it gets like effervescent bubbles right here. This one didn't. Oh, that's an interesting look. Kind of looks like an upside down omega or a bead of water on an Eve or something, or the little uvula in the back of your throat. That's what it is. It's your uvula. Okay. And we want to know what is the slope at 1, negative 3. So 1, negative 3 is going to be about right. 1, 2. 1, negative 3 is going to be right around here. It's going to be right there at that fingertip. Right there, if you were to draw the tangent line, it would be pretty flat, right? But still positive. Guess what the slope of that graph is right there? 1/8. Yeah. Hey, look. This graph looks like it has 2 vertical tangents, doesn't it? You see those little turning points side to side? Those would be vertical tangents, yes? It also looks like it has 1 horizontal tangent. What do you think the x value is of the horizontal tangent? It looks like it's 0. Can we verify that with our equation? Yeah. Remember, the derivative is a fraction. And when is a fraction equal to 0? Only when the numerator is equal to 0. So if you just set the numerator equal to 0 and solve, you get 2x equals 0. That means x equals 0. So we were correct. When do you get vertical tangents? Yeah, 0 over non-zero equals 0. Okay, but non-zero over 0 equals plus or minus infinity. Well, that would be setting the denominator equal to 0. The denominator is a quadratic, which means it has how many roots? Up to 2. How many vertical tangents did the graph appear to have? 2. Yeah. So we're actually going to be doing that later on. We're going to be setting the numerator equal to 0 to find horizontal tangents, and we're going to be setting the denominator equal to find the vertical tangents. But right now, we're just kind of looking at it and going, oh, cool, neato, mosquito. Any comments or questions on any of those examples so far? It's National Knee Day. Did you know that? That's pretty cool. Y'all didn't know that. I told you at the beginning of class. Knee Day. How do you celebrate Knee Day? Bend your knee. You bend your knee, right? You don't walk like this like you usually do. Today, you actually bend your knees when you walk. Yeah. Yeah. Did y'all ever like ride a bike when you were young and you started pedaling real fast and the chain came off and your knee slipped off the pedal and rammed into the handlebars? That ever happened to y'all? That is painful. Ouch. I did that like 100 times. Yeah, I broke my kneecaps a couple of times growing up. So anyway, I'm celebrating my knees today by creaking along. Right? If you hear me creaking along, it's my knees. No, I don't have metal kneecaps. But my knees are pretty much shot. So anyway, I'm glad I'm still just young.